Hello students, in this video of linear algebra revision, first we will start with the types of matrices. First, coming to scalar matrix, a matrix is said to be scalar if it is a diagonal matrix and all the diagonal elements are equal. Suppose -1, -1, 0, 0. This is a diagonal matrix and the diagonal elements are equal, so this is a scalar matrix. And a matrix is said to be symmetric if its transpose equal to A. If A transpose equal to A, it is symmetric. If A transpose equal to minus A, it is skew-symmetric. And if A square equal to A, it is said to be idempotent matrix. If A square equal to I, then it is said to be involuntary matrix. If A power m equal to 0, then A is said to be nilpotent and m is called as the order of the null matrix. And if A into A transpose equal to I, this is called as orthogonal matrix. I can write this as A transpose equal to A inverse. While coming to Hermitian, I should define A power theta, which is transpose of the conjugate matrix. This is called as A power theta. If A theta equal to A, then it is called as Hermitian matrix. If A theta equal to minus A, then it is called as skew-Hermitian. Similarly, if A into A theta equal to I, then it is called as unitary matrix. The properties of orthogonal and the properties of unitary matrix both will be similar while dealing with eigenvalues and eigenvectors. And if we see the periodic, if A power k plus 1 equal to A, then K is called as the period of that matrix. If you see the idempotent matrix A square equal to A, I can write this as A power 1 plus 1 equal to A. Here I can tell that 1 is the period of idempotent matrix. What is the period of this idempotent matrix? 1, right? Now we will see the properties of symmetric and skew-symmetric matrix. Suppose if A and B are two symmetric matrices, then A power k plus or minus B power k is also a symmetric matrix. AB plus PA is also a symmetric matrix, but AB minus PA is a skew-symmetric matrix. Similarly, if A and B are skew-symmetric matrices, A power k plus or minus B power k. Here you will have two cases. If k is even, if k is odd. If k is even, A power k plus or minus B power k will become symmetric matrix. If k is odd, A power k plus or minus B power k will still remain as skew-symmetric matrix. Is this okay? Next, there is a property that every square matrix can be expressed as sum of symmetric and skew-symmetric matrices. If A is a square matrix, then A plus A transpose will become symmetric matrix. A minus A transpose will become skew-symmetric matrix. We can write A as A plus A transpose by 2 plus A minus A transpose by 2. This is symmetric matrix, this is skew-symmetric matrix. And if you see the properties of Hermitian matrix, A theta whole theta will be equal to A. What is A theta? A conjugate whole transpose. Next, A plus B whole theta is equal to A theta plus B theta. Ka whole theta is equal to K conjugate into A power theta. And AB whole theta is equal to B theta into A theta. If you don't remember this, just substitute A conjugate whole transpose in place of A and you will get all result. If you see the multiplication of matrices, if A is a matrix of order m cross n and B is of n cross p, then number of multiplications and number of additions in the matrix A into B? The answer is number of multiplications will be m into n into p, while number of additions will be m into p into n minus 1. GATE will not ask this question, but the other PSUs will ask. And while coming to determinant, I am assuming that you people know how to calculate the determinants. We will just see some of the important properties, right? Determinant of a power m will be det a whole power m, and determinant of a into b will be det a into det b. Determinant of A inverse will be 1 by det A, and determinant of A and A transpose both are same. If you multiply each element in the matrix A with a scalar constant k, then its determinant will become n times the det of A. Next, while coming to orthogonal and unitary matrix, I already told that both properties will be same. Orthogonal is A into A transpose equal to I, while unitary matrix is A into A Hermitian equal to I. Right? The det of orthogonal matrix is plus or minus 1. The det of unitary matrix will be plus or minus 1. And while coming to idempotent matrix, which A square equal to A, the det of idempotent matrix will be either 0 or 1. And if A is a skew-symmetric matrix of odd order, I mean 3 cross 3 or 5 cross 5 like this, then its det will be 0. For a matrix to be skew-symmetric, its diagonal elements should be either 0 or purely imaginary. You know this, right? It is very important property. And A transpose equal to minus A, you know this, but remember this property, diagonal element should be 0 or purely imaginary. And while coming to adjoint matrix, you know that A inverse equal to adjoint A by det A. I hope you know how to calculate adjoint A, cofactor matrix and everything. I will concentrate on main properties. Adjoint of AB will be equal to adjoint of A into adjoint of B. If you see the det of adjoint matrix, this will be equal to det A power n minus 1, where n is the order of matrix A. Now, if you see the det of adjacent A, what we are doing, we are substituting adjacent A in place of A. Now I can write this as, in place of A I am substituting adjacent A power n minus 1. Det of adjacent A will be again det A power n minus 1. So it will become n minus 1 whole square. Like this we should calculate. And adjacent of adjacent A without any det will be equal to det A power n minus 2. See, here there are two terms, so n minus 2 into A, and adjacent of A Hermitian will be equal to adjacent A of whole Hermitian. This is not that much important, you can neglect, but the above properties in the normal PSU exams, they are very important. While coming to inverse of a matrix, if det A equal to 0, it is called as singular matrix. If det A not equal to 0, this is called as non-singular matrix. And Ka whole inverse will be equal to A inverse by K. If you see the inverse of a diagonal matrix like A, this will be equal to 1 by A, 1 by B, 1 by C. Remember this property. Determinant of A, inverse of A diagonal matrix. If this is equal to A, provided that det A is not equal to 0. And I hope you know this remaining properties like AB whole inverse equal to B inverse into A inverse. These are very basic properties you should know. And if two rows or two columns are interchanged, then the determinant will be multiplied by -1. I forgot to say this. While coming to the vectors, suppose x1 is some vector and x2 is some vector. Then if x1 transpose into x2 equal to 0, then it is called as orthogonal vector. If along with this x1 transpose into x1 and x2 transpose into x2, if the values of these vectors is equal to 1, then the whole set is called as orthonormal vector. And the most important topic in linear algebra, system of linear equations. 70% the question will be framed from this topic. See, in this you will have two types. One is non-homogeneous equations. Second one is homogeneous equations. The type of the equations Ax equal to B are called non-homogeneous. The type of the equations Ax equal to 0 are called as homogeneous equation. While coming to the solution of non-homogeneous equation, you should find the rank of A, you should find the rank of AB. If rank of A equal to rank of AB equal to n, where n is the order of the matrix A, then it will have unique solution. I mean one solution. If rank of A equal to rank of AB less than n, then it will have infinite number of solutions. If rank of A not equal to rank of AB, then it will have no solution. It will not have any solution, right? And while coming to homogeneous, if rank of A equal to n, where n is the order of the matrix A, then it will have unique solution. See, there are many names for this, and that unique solution itself is a zero solution. I mean x1 equal to x2 equal to x3 will be 0. This is the solution. It will have unique solution and that solution is a zero solution. So zero solution, and it is also called as trivial solution. Trivial solution and one solution. And what is that solution? The answer will be 0. If rank of A less than n, then there will be infinite number of solutions. If you see the first case, rank of A equal to n, it will have the 0 solution. So I can tell that these are linearly independent. Linearly independent. So if rank of A equal to n, I can tell that det A is not equal to 0. So the condition for the three vectors, suppose in the question he mentioned three vectors and he asked that they are linearly independent, what is the condition? Det A should be not equal to 0, then they are linearly independent. If you see this case, they are linearly dependent. And the condition for linearly dependency is det A should be equal to 0. If det A equal to 0, then only rank A will be less than n, right? In this case, the most important question is find the number of linearly independent solutions. See, there will be infinite number of solutions. In that, you will have n minus r linearly independent solution. Remaining all will be linearly dependent, where R is the rank of the matrix. It will be like if 1, 2, 3 is one linearly independent solution, the remaining all solutions will be like 2, 4, 6, 3, 6, 9, like 1k, 2k, 3k. Only 1, 2, 3 is independent, remaining all solutions are dependent on this. For calculating number of linearly independent, the formula is n minus r. While calculating the eigenvectors, the properties which we have discussed in the homogeneous equations are all applicable to eigenvectors. Why? Because eigenvectors will be of the form a minus lambda I into x equal to 0. If I replace a minus lambda I by some value b, then it will become b into x equal to 0. Now x is our eigenvector. The properties of all homogeneous equations, the properties of homogeneous equations are applicable to the properties that are related to eigenvectors. Next topic is eigenvalues and eigenvectors. If A is a square matrix of order n cross n, then A minus lambda is called as characteristic equation. This is characteristic equation, and the roots of characteristic equation will be eigenvalues. If lambda 1, lambda 2, lambda 3 are the eigenvalues, for each eigenvalue there exists an eigenvector. X is called as eigenvector. Suppose for lambda 1, a minus lambda 1 into I equal to 0, I into x equal to 0. Let this be x1. There exists an eigenvector. And for the value lambda 2, there exists another vector. Similarly for the value lambda 3. Now if you see the properties of eigenvalues, sum of all the eigenvalues will be equal to trace of A. Product of all the eigenvalues will be equal to det of A. And if lambda is the eigenvalue of A, then for A power m, eigenvalue is lambda power m. For Ka, k lambda. For A plus Ki, lambda plus k. For A minus Ki, lambda minus k. For this, A0 plus A1 lambda plus A2 into lambda square. For A inverse, eigenvalue is 1 by lambda. For adjacent A, see A inverse will be equal to adjacent A by det A. This det A will go here. For adjacent A, it will be equal to det A by lambda. And if A plus root b is an eigenvalue, then A minus root b should also be an eigenvalue. If A plus ib is an eigenvalue, then A minus ib should also be an eigenvalue. And these three properties are very important properties. These three properties you should by heart. They can be directly asked for 1 mark in some PSU exam. The eigenvalues of symmetric matrix or Hermitian matrix are purely real. What is symmetric matrix? A transpose equal to A. What is Hermitian matrix? A theta equal to A. And the eigenvalues of skew symmetric or skew Hermitian or 0 or purely imaginary. And the eigenvalues of orthogonal matrix or unitary matrix or of unit modulus. If you take the modulus of eigenvalues, it will be equal to 1. What is an orthogonal matrix? A transpose equal to A inverse. A into A transpose equal to I. What is unitary matrix? A into A theta equal to Y. These three are very important properties. While coming to eigenvectors, the first step is you should find the eigenvalues. After finding the eigenvalues, you should substitute in this equation a minus lambda I into x equal to 0. For each eigenvalue lambda, you will have an eigenvector. Suppose lambda is equal to 1, 2, 3. A minus I into x equal to 0. X is our eigenvector. Suppose the answer of A minus I is B. B into x equal to 0. Now it is nothing but a homogeneous equation. In this homogeneous equation, you can find number of linearly independent eigenvectors, right? Which is equal to n minus r linearly independent eigenvectors. See, for lambda equal to 1, Suppose you are getting two linearly independent eigenvectors. Next, substitute lambda equal to 2. That is a minus 2y. Let it be equal to c. This will be c into x equal to 0. And again find the number of linearly independent eigenvectors. That is n minus r. Suppose the answer is 1 linearly independent. And next, substitute lambda equal to 3. Let this be d into x equal to 0. Suppose n minus r is 0. Rank of t is equal to n. Then what are the total number of linearly independent eigenvectors? For lambda equal to 1 you are getting 2. And for lambda equal to 2 you are getting 1. For lambda equal to 3 you are getting 0. Plus 0. So there are totally 3 linearly independent eigenvectors. But in some questions the eigenvalues will be repeated. How to handle that kind of questions? Suppose the eigenvalues are lambda equal to 1, 1, 2. If you substitute lambda equal to 1, it will be a minus I into x equal to 0. You will get the value of x. If you substitute the another value of lambda, that is 1, you will get the another values of x. Let this be x1, let this be x2. x1 will be equal to x2, right? Why? Here also a minus I will be there. Here also a minus y will be there. Why? Because lambda is equal to 1. Suppose for this matrix you are having two linearly independent eigenvectors. For x2 is also having two linearly independent eigenvectors. And these two linearly independent eigenvectors are same, right? If these two linearly independent eigenvectors are same, then I shouldn't write 2 plus 2. Only 2 is enough. Why? These two vectors are again coming from these two vectors. Both are same. If it is having two linearly independent eigenvectors, then leave this. Directly go for this. If it is having one linearly independent eigenvectors, the total number of linearly independent eigenvectors are 2 plus 1. That is equal to 3, right? The next concept is algebraic multiplicity and geometric multiplicity. If the eigenvalues are 1, 1, 2, then algebraic multiplicity of 1 is 2. Why? Because it is repeating 2 times. And while coming to geometric multiplicity, if the eigenvalue 1 is having 2 linearly independent eigenvectors, then GM will be 2. GM is nothing but number of linearly independent eigenvectors. It is calculated for each eigenvalue. And AM is also calculated for each eigenvalue, but how many times the eigenvalue is repeated. That is the AM. And the condition is AM should always be greater than GM or equal to. If the eigenvectors of A are x1, x2, x3, then the eigenvectors of A power m, A inverse, and these two matrices, they all will be same. That is x1, x2, x3. Eigenvalues will be changed, but eigenvectors will not change. And here the important property is A and A transpose. Eigenvectors of A and A transpose are not same, while eigenvalues of A and A transpose are same. You should remember this. In the option A, he can give that eigenvalues and eigenvectors are same. Eigenvalues are same, but eigenvectors are not same. Eigenvectors are same, but eigenvalues are not same. Like that, he can mention. We should remember this. Eigenvalues are same, but eigenvectors are not same. With this, the important points on eigenvectors is completed. The last topic is Cayley-Hamilton theorem. It states that every square matrix will satisfy its own characteristic equation. Suppose lambda cube minus 11 lambda square plus 5 lambda plus 2 is a characteristic equation of A. Then A should satisfy this. A cube minus 11a square plus 5a plus 2 equal to 0. 2 into I equal to 0. A should satisfy this characteristic equation. And this theorem is used to find inverse of matrix and high powers of matrix. With this, the revision lecture is completed. If you just watch this video, the marks you will get is 0. Why? Because mathematics needs practice. For each topic, at least practice 2 to 3 questions and be prepared. Then only you can score good marks in maths. That's it, guys. If you like this video, hit the like button, and for more revision videos, do subscribe to my channel. Thank you.